Okay, so let's keep going. All right. Like I said, let's look at a problem. Okay. So let's see. Let's look at this problem here in the book. The phase voltage. See, this is just so you can follow along. Probably easier to read. Page 405 in your book. All right. This problem 11.3 right here. The phase voltage at the terminals of a balanced three-phase Y-connected load is 2400 volts. Now, let's talk about this for a second. It's 2400 volts. This is, for the most part, on RMS value, not peak values, RMS values. That's typically what we use in our analysis, again, because it makes our power equations easier. Okay? So most likely, we're going to assume that this is an RMS value. All right, the phase voltage at the terminals of a balanced three-phase Y-connected load is 2400 volts. Okay, so let's draw that. Okay, so this is assessment problem 11.3. Okay, so this is page 405. Okay, in the book. All right, with phase voltages at the terminals of a balanced three-phase Y-connected load is 2400 volts. Okay, so let's draw our load. All right. Now this term phase voltage, I should probably define a couple of things here before I go too far. Okay. I hate the terms, but they're important, so let me go over them real quick. All right, they get confusing very quickly. All right, line voltage and phase voltage. Okay. All right. Line voltage refers to voltage between two lines. Phase voltage is voltage across a single phase. Okay, confusing a little bit. Okay, let's look at what that means. If I have a Y connection, all right, so if I have a Y connection, each of these, okay, each of these is a phase. All right, each of those is a single phase of a three-phase load. Okay, so the phase voltage would be the voltage across that phase. This is a phase voltage right here. This is a phase voltage. This is a phase voltage. The voltage across one of these is a phase voltage. Line voltage is the voltage from here to here. Okay, from this line to this line. So if this is A, this is B, this is C, the voltage from A to B is the line voltage. Okay, generally you'll hear me say line to line voltage so as not to confuse you. Now, where does this get confusing? Now, if I look at a delta connection of loads, if a load is delta connected, okay, and it could be, all right. For instance, a load could be a three-phase motor. And a three-phase motor could be either, each of the three phases could either be Y connected or delta connected. Doesn't matter. Okay, it'll work the same either way. All right. Each of these, this is a phase now. Okay, each of the impedances there is a phase. In this case, the phase voltage is the voltage across this phase. That is the same as the voltage between the two lines. Okay? So I guess what I can say is, maybe here's how I should write this. Okay. In a delta circuit, these are the same, the line voltage and the phase voltage. In a Y, they're different. Okay. In a Y, the line voltage is V line to line. In this guy, the phase voltage is V line to neutral. All right. It's kind of a silly set of words to think about, right? But basically, in the Y setup, phase voltage is the volt. So maybe the key thing to say here is is to remember that each of these things, this, each of those is a phase. Okay. The voltage across a phase is the phase voltage. The voltage between points A and B, or points B and C, or C and A, is a line voltage. In a delta connection, line to line voltage, or line voltage, is the same as phase voltage. Okay, in a delta, they're the same. In a Y, they're different. Okay, if I talked about currents, okay, line current is current in a line. Okay, phase current is current in a phase. Okay. All right. So if I had a delta, or sorry, a Y, I'm going to do Y first. Okay. So each of these legs here is a phase. In this case, this is the A line, this is the B line, this is the C line. In this case, the current in each phase and the current in each line is the same. If I looked at a delta, okay, if I looked at a delta, all right, let's call this A, let's call this B, and let's call this C. This current here would be I line, all right. This would be I phase, all right. So in this case, in Y, line current and phase current are the same, and in delta, they're different. In delta, line current is here. Phase current is the current actually flowing in each phase. Okay. All right. So we'll look at some examples of that. We'll come back to that set of definitions. All right. That's important to do. Let me quickly just run through that. Line voltage is voltage between two lines. Phase voltage is voltage across a single phase. Okay. And the term phase refers to each of the impedances, or each of the source impedance combinations. Okay. Line currents, the current in a line. Phase currents, current in a phase. So in a Y connection, the line current and phase current are going to be the same. In a delta connection, this is the line current, this is the phase current. Okay, we'll look at some relationships on that as we go. All right. So back to the problem again. 11.3, page 405 here. All right. So page 405, 11.3. All right. So we're told that the phase voltage at the terminals of a balanced three-phase connected load is 2400 volts. Okay. So what does that mean? All right, well, it's balanced. So I'm going to say that this is 2400 volts. And again, I'm going to assume that's RMS. All right, because that's sort of the typical thing that we're going to have. All right, now, in this case, all right, I'm going to call that, if I call this, just trying to understand exactly how they did this. Okay, I guess they're calling this A, B, and C, okay, with capital letters. All right, that tells me this guy is, it's 2400 volts. Okay, there's 2400 volts across each of these. Now the phases are different. All right, I'm going to get to the phases as I go. All right, I'm going to keep reading the problem. All right, the load has an impedance of 16 plus J 12 ohms per phase. Okay, so they've told me that this guy right here, I'm going to call that ZY, okay, which is the same for each of these guys. Okay, they've told me that ZY equals 16 plus J12. Okay, so that tells me this guy has to be, just refresh our memory, inductive, right? He's got some inductive impedance, because remember, impedance J omega L. If it's positive there, that means it's got to be an inductive load, which means I could also say it's lagging, right? This guy's going to have a lagging power factor if we eventually get to that, okay? All right. What else are we told? The load has an impedance of 16 plus J12. We've got that. And it's fed from a line having an impedance of 0.1 plus J0.8 per phase. Okay. All right, so that means that each of these guys is fed from a line having some impedance. Okay, I'm going to call this Z line, Z line, Z line, right? And I'm going to say that Z line equals, what does it say? 0.1 plus J times 0.8. Okay, also inductive, right? Because it's got the positive imaginary part. All right, the Y-connected source at the sending end of the line, all right, where the sources are. So the sources are Y-connected, have a sequence of ACB, okay? So that's an ACB, that means it's a negative sequence set, okay? So what was the difference between the positive sequence and the negative sequence? All right, ACB, what that meant is A peaked first, C peaked second, B peaked third, right? In terms of our phasors, that means VA is V. VC is V with a phase shift of negative 120 degrees. He's 120 degrees behind him. And VB is 240 degrees behind. Okay? All right? They're just trying to make it more confusing. All right, so let's keep going. We know that that's the way things are going to go in this particular case. So, all right, we're also told that each source has an internal impedance. Okay, so let's see if I can kind of draw that cleanly over here. All right, here's VA with an internal impedance. All right, connected to here. All right, and let's go to my neutral point. All right, here is our C phase connection, also with an internal impedance. And here is my B phase connection, all right, also with an internal impedance. Okay. All right, so since I have that negative sequence set, let's keep writing down all the key things here. Let's call this Z source. I'm going to call it ZS for Z source, and it's the same for each of these. According to what we're told in this problem, again, you can find on page 405, internal impedance of 0.02 plus J times 0.16. Okay. All right, now, because it's that negative sequence, we know that VA is V. We don't know what it is. We're not told what it is in this case. VB is V, and he's behind by 240 degrees, right? And VC is behind by 120 degrees. So again, this would be for what we call an ACB, or negative sequence set. Okay? All right. Now let's label some points because they do that. Here's sort of a typical way that we might do this. I'm going to call this here point A, point C, and point B. and it looks like what they're trying to refer to is some point internal. All right, so this point here as C prime, B prime, and A prime, and that as N, and this as capital N. Okay? All right. Okay. All right. So what are they asking for? Use the A phase voltage at the load as the reference. Okay, now I should be careful about this, all right? Let me be a little more careful about how I define this because I see now use A phase voltage at the load as the reference. All right, when they say that's the reference, okay, that means that this is the guy we're defining to have 0 degrees here, okay? That means these guys are going to have to be out of phase with respect to this, okay, to say that this is the reference. So I don't know, this guy I'm going to say has some phase shift phi. He will also have this phase shift phi. He will also have this phase shift phi, okay? Now what we want to do to solve anything in these particular problems is get an equivalent single phase circuit. Okay, so how do we get that? Well, let's look at A phase. All right, what we see, if I look at A phase, here's VA, okay, the source. I can just draw out for myself. If I look at it, right, follow a current leaving A phase. It goes out through here, through this Z source, through Z line, through ZY. Now in the equivalent single phase circuit, I can just say I have this. Okay. All I have to do is solve for the currents in this circuit and voltages, whatever, and I can just map that with the right phase shifts to the circuits the B and C circuits. Okay, so let's label the points. This was A prime. This was A. This was capital A. Okay. All right. So let's see. So here again, A prime A, capital A. A prime A, capital A. All right. So we're told to calculate the line currents I little a, big A. So that's, and again, basically that's the line current here is the current going through this impedance, through this line impedance. Okay, this is pretty easy to do here. Okay, why? Because I know in this case that what is it going to be? Well, it's pretty simple. I just have to say that it's basically, what do I know? I know this voltage here, 2400, right? Okay, so they ask me what are I, I, B, B, I, C, C. Okay, that's the current. Yeah, that's the current here, and the current there. Okay, which is the current in the equivalent single phase circuit. Now, in this case, I've been told this impedance. I've been told all the impedances, I guess. The only thing I've been told about the voltages is what this voltage is here at the load end. Okay, 2400. So let's do it. Okay, in this case, IAA. Okay, let's find that phasor. Okay, well that's pretty simple. It's just going to be 2400 volts divided by ZY. Okay, and ZY we were told was 16 plus J12. Okay. All right. So IAA is 2400 divided by 16 plus J12. Okay. All right. So what does that give us? Okay. Well, that's 2400 divided by 16 squared plus 12 squared. Okay. There's e to the j. All right, what's the angle of the top? Angle of the top is 0 degrees minus the angle of the bottom. Okay. So minus the angle of 16 plus j 12. All right, so let's work that out. All right. So we're going to fire this up in MATLAB here. So 2400 divided by the square root of 16 squared plus 12 squared. All right, is 120. Okay. Now, angle-wise, all right, angle-wise, a tan of, that's the way MATLAB does arctan. The imaginary part is 12. The real part is 16. Right, and it said negative. Okay, now that's in radians. MATLAB does it in radians by default, so let's convert that to degrees. Negative 36.87 degrees. Okay. So let's go back to the display here. Okay. So e to the j negative 36.87 degrees. Okay, which matches what the book tells us. Okay. All right. So now, question becomes, how do I get IBB and ICC? Do I have to do work to do this? Not really, right? If I've got a balanced load, I don't need to solve. I mean, I could draw the single phase equivalent circuit, do all that, but I don't have to, right? In this case, I know it's going to have the same magnitude because everything is balanced. Question is, and so the same is true for ICC. That will also be a magnitude of 120. The question is, how do I get to what the angle is in this case? Okay, how do I get to what the angle is going to be? Okay, well, because I've said this is a negative sequence set rather than a positive sequence set, here's what I do. All right. I'm going to say, in this case, that this is got the same angle, all right, minus another 120 degrees. Okay. Now, minus another 120 degrees because this guy, the C phase, is behind A phase by 120 degrees. On B, okay, he's behind by 240 degrees. Now, this is not normal, right? This is what we would have for a negative sequence set, or an ACB connection, which is what they're talking about. All right, so let's see what that gives us in each of these cases. For this guy, I get 120. All right, and I do minus 36.87 minus 240. All right, that gives me e to the minus j 276.87. Okay. And for this one, it gives me 120 with an angle of negative 156.87. Now, if I look at what the book has for solutions, this is correct, this is the same, but it's different for this one. They say it has an angle of 83.13 degrees. Yeah, that's the same thing, right? If I do 360 minus 276.87, I get 83.13. Remember, I can give either a positive angle or a negative angle, right? If I have an angle of negative 120, that's the same as positive 240, right? And so you see the book has a different answer for this one, right? Because instead of subtracting 240, they added 120, right? And which is perfectly fine to do as well. Okay? All right, so again, what did we do? Let's follow the process. We created a single phase equivalent circuit. Okay? I take that single phase equivalent circuit. In this case, I knew this voltage. I solved for this current by doing 2400 divided by that impedance. All right? That was pretty easy to do. To map that over to the B phase and the C phase, right? To map that over to B and C phase, I know that the magnitude has to be the same for those currents. All right, magnitudes have to be the same. The angles had to be shifted by 120 degrees each way. Okay, so then I just had to think about which direction it was. In this case, it was a little strange because I was told it was an ACB or a negative sequence set. Excuse me. All right, so let's keep going. All right, now part B of that problem, we are told to find the line voltages at the source, okay? The line voltages at the source. So line voltages, remember, is always voltage between two lines. All right, so that means find VAB and VBC and VCA, okay? Now, this is a little tricky now because, again, what they're saying essentially is when they're talking about those voltages, they're saying this has an internal impedance in here, okay? So that means I got to take into account what that impedance is. So back to our single phase equivalent circuit, all right? Let's go to our single phase equivalent circuit, all right? Now, the simplest thing for me to do probably in this thing is to say, all right, let's find in our single phase equivalent circuit what VAN is. All right, so VAN. Once I know that, I can use that to convert to the line-to-line voltage, okay? Because we know the relationship between line-to-line voltage and line-to-neutral voltage. How do I do that? Well, I don't know what this voltage is just yet, but what I do know is what this current is. And so I know from looking at that circuit, right? If I look at that circuit, I know that by KVL, right, if I define this as VAN, I know that VAN must be IAA, the current going through here, times Z line plus ZY. Okay? Right? I don't need to know what this is. Essentially, by KCL, if I know the voltage across here, I know the voltage across the other half of the circuit. All right, sorry, by KVL. If I know the voltage across one half, I always know the voltage across the other half. By KVL, they have to be equal. All right, so what do I know about those guys? All right, so I know IAA is 120 e to the minus j 36.87 degrees. Okay. Now, what was I told about Z line? I was told that Z line was 0.1 plus j times 0.8. All right. And ZY supposedly is, in this case, what was ZY? It was 16 plus j 12. Like that. Okay. All right. So I gotta figure out what to do here. So the simplest thing for me, I'm gonna try to convert this guy here over to rectangular, or sorry, to polar coordinates. Okay. So 120 e to the minus j 36.87 degrees. All right, this becomes 16.1, it looks like. 16.1 plus 12.8 j. All right, so let's convert that to polar. Okay, so 16.1 squared plus 12.8. All right, 16.1 squared plus 12.8 squared Alright, and take square root of that. So 20.57. Alright, so this becomes 20.57. Okay. With an angle of, let's see, inverse tan of the imaginary part is 12.8 divided by 16.1. E to the j 38 point, looks like 49 degrees. Okay. All right, now that's pretty easy to multiply. All right, so when I multiply those two guys, I have 120 times 20.57. All right, that works out to be 2468.4. All right, 2468.4. With an angle, for the angles I just add, so I get 30, I get 38.49 minus 36.87, and that becomes 1.62 degrees, like that. All right. Now, what have I found? I have found VAN. Okay. Now, what was I asked to find? I was asked to find, remember, I was asked to find in this problem VAB, VBC, and VCA. All right? Those were the things I was asked to find. What I found now is VAN. All right? Well, what can I do to find these guys? Well, I can keep going and I can say VBN and VCN. What are those equal to? Well, because everything's balanced, I know that these have to be the same magnitude, 2468.4, 2468.4. Now the angles, let's see. All right, again, because it's a negative sequence set, I know that this guy is 120 behind, so C is 120 behind A. So I go 1.62 degrees, right? 1.62 minus 120 tells me that this guy has an angle of minus J times 118.38. Okay, 118.38. Okay, he's 120 degrees behind. This guy's 240 degrees behind, so I do 1.62 minus 240, and that gives me e to the minus j 238.38 degrees. Okay, all right. Now, that's VAN. VAN is this guy. VBN is this guy. VCN is this guy. Now, how do I go about finding? Okay, let's sketch those. All right, let's sketch those guys. Where's VAN? Well, VAN is right about there. Okay. All right, where is VCN? VCN is somewhere over here. All right. And VBN is somewhere over here. Okay. Now, what do I know about my line-to-line voltages? Well, I've got one that's ahead by 30 degrees here. I got one that's ahead by 30 degrees here. And I've got one that's ahead by 30 degrees here. Okay, so 30 degrees, 30 degrees, 30 degrees. Okay, now which ones, they're ahead by 30 degrees and they're also square root of 3 longer. Okay, So in this case, this one here is VAC. This is VCB. And this is VBA. Okay? All right. All right. So what are they? Well, VAC is square root of 3 times 2468.4. Right? So square root of 3. Because again, the magnitudes of the line-to-line voltages have to be square root 3 longer, square root 3 bigger than the line to neutral voltages. Right? So if I do square root of 3 times 2468.4, I get 4275. 4275 point, looks like 0.4, which is pretty close to what they've got there in the book. Now, what's the angle that I get for that? All right. So for VAC, all right, the angle of this is going to be 30 degrees ahead of this one. So 30 degrees plus 1.62, so 31.62 degrees. Now, what they actually asked me for is VCA. All right, VCA. Well, where is VCA going to be? VCA should be the opposite of this guy. All right, VCA is the opposite of this guy. So what's opposite of mean? It means subtract 180 degrees from this guy. So 31.62 minus 180 degrees. All right, is minus 148.38. Okay, so 4275.4. All right, and the angle is 31.62 minus 180. Minus 180. Okay, which works out to 4275.4 e to the j minus 148.38. Okay, which if you look in the book, all right, my magnitudes are a little different. They have 4275.02. Okay, pretty close, a rounding error, right? But they have the same angle, 148.38. Okay, so if I went through a similar way, right, I'd follow that same approach here, right? I would say VBA, okay, is root 3 times VBN, okay, and then I advance this guy by 30 degrees. All right, so I add another 30 degrees, okay, and to find VAB, what they really want, I take VBA and I subtract 180 degrees from it. Okay? Same basic approach. If I go through that, I'm going to find essentially this becomes, right, this becomes 4275.4. And I'm going to find that the angle for VAB is minus 28.38. Okay. And if I follow that same approach for the other one, so VCB, okay, looking at the picture, VCB is 30 degrees ahead of VCN, all right, root 3 times VCN, okay, so that's how I change the magnitude, multiply by root 3, and then I add another 30 degrees to it, okay, and then I try to find, sorry, what they actually asked me for, VBC, VBC is VCB, what I found here, and I got to subtract 180 degrees, okay, since it's BC instead of CB, okay? And if I go through that process, I'm going to find the same thing, same magnitude, 4275.4, and my angle for VBC is going to be 91.62 degrees, okay? All right, that's part B. All right, what was part C? Part C of this problem is now to find the internal phase to neutral voltages at the source, okay? Internal phase to neutral voltages at the source. That's actually a lot easier, okay? So in that case, what are the internal phase to neutral? That's this A prime to N. So for C, VA prime N, okay? Again, what's that going to be? Well, by KVL, it's going to be IA, okay, times ZS plus Z line plus ZY, okay. That's really not too hard to do, okay. If you go through that according to the book, not surprisingly, okay, it's going to be 2482, they say 2482.05 with an angle of 1.93 degrees, okay. And it wouldn't be too hard now. What would I do to get VB prime N and VC prime N, right? What do I do? Each of these is going to have the same magnitude, right? So 2482.05, 2482.05, all right. 1.93. Now this guy is, because it's a negative sequence set, the B phase is behind by 240 degrees. And C phase is behind by 120 degrees. Okay? And that should match pretty closely with what they have. Okay? And it does. All right?